So, first, our little quiz here. Describe one way to do classification plus localization, and that's something we talked about last time.
Yeah, so we can use the convolution and pooling for that, and then use like two different fully connected layers to implement the classification and then localization. And then we can use the I like the what's it called the IOU, the interleave over union to find the evaluation and then do that.
Very good, very good. Yeah, so we're using one head of the neural network to act as uh, the part that finds the rectangle around the item,
Hmm.
and we use the other one to actually classify the item, and finally we have a uh, that IOU loss function that's going to help us actually do that. Who was that?
Karthik, Kartik.
Cool, cool, cool. All right. Um, so again, today we're talking about style transfer. This is some cool stuff. What did I say? We need to schedule style transfer lab and free day. Oh, I don't know what that is. That's probably from a previous semester where I added it and forgot to take it out. So ignore that part. It's just the style transfer today. Um, so the task we're working with here is we have an input that's going to be a content image and a style image. So that could be a picture of you as the content image and a picture of a artwork that's drawn in a certain abstract style. And the output that we're looking for here is a third image that has the content of the content image and the style of the style image. So in this case, let's say content image is a dog, style image is um, well, the one we use here a lot is Starry Night. So we want to get a dog that looks like it was drawn in the style of Starry Night. So that's our goal, and it's a difficult goal, and there's been a lot of work put into accomplishing it. Here are some examples of that are written using the same system that you'll be using today or in the next week, 2 weeks. Um, we have this picture of a glacial mountainside, and we've applied two images to it as style images. So here's our content image. We applied these two style images, and from that we were able to produce these. And you can see that it's definitely started learning the style here. And with this one, it had a harder time um, uh, transferring the simple curves and simple lines of this sort of almost cartoony looking drawing. But it was able to realize that it needed those, so it actually started to try to create these mountains made in this cartoony fashion. Um, and in the same way, it was able to take the swirls and darker colors of Starry Night here and apply those in the same way to produce this image. I like both of them a lot. I actually think I like this one more just because it looks like some sort of trippy dreamscape. Um, I'm a fan of this one a lot. Um, there's lots of ways to do this though. GANs are probably the most effective right now. A certain type of GAN. There's one called Style GAN that is insane. Style GAN is nuts. It can turn one thing it can do is take a video of a horse and turn it into a video of a zebra. Or it can do stuff like taking a picture in summer and making it look like winter. And again, this is without um, it's without taking two pictures of it. It's doing a sort of self supervised learning. Um, that said, today we're going to use a bit of a simpler way of doing this in a kind of hacky way, and I kind of like it for that reason. There's this paper. This is a neural algorithm of artistic style. Oops. And the method it uses is based on this fact we've talked about previously, that CNNs build up these patterns inside of themselves hierarchically. And it uses that attribute to reconcile from content, which is exactly what we want here. We need to split away the content and the style from each of these so we can recombine them into one. And in a lot of ways, when we actually get into the lab for this, we have skeleton code as usual, and in fact, we have a lot of skeleton code. If you want to follow that pretty closely, you can almost treat it like a fill in the blank sort of thing, where it's just a few lines at a time and that sort of thing. We have a lot of code we give you. But if you find that, personally, I can sometimes find that more confusing. So if you want to start blank template and just erase a lot of it, that's totally fine too if you want to take it a different way. The only thing that we're going to insist on is that the algorithm you use is this one, the one in this paper, which is helpful because it's a good algorithm. And the key finding of this paper, and this is directly from their abstract, I think, is that the representation of content and style in convolutional neural networks are separable. That is, we can manipulate both representations independently to produce new, perceptually meaningful images. That's important. This is the paper summed up in a lot of ways. They're saying we have a way, or their contribution is that we have a way of separating content and style through a CNN. And with that, recombining should be more trivial. So again, we've seen this before. I'm just going over it again. As we build up our neural network, as we go up layers in the convolutional scheme here, we begin to capture in these filters, in these output activation maps, we begin to capture more detailed, more importance probably not the right word, more complex features inside of the image. So earlier on, we're just looking at lines and circles and very small level features of the image. And later on, layer 2, we have whole sections of the face. We have eyes and noses and things like that. And then finally, we get up to layer 3, where we're reconstructing whole faces here. So that's the idea. As we go up in the network, we are looking at more complex abstractions. So the core idea here is that if you have a well-trained convolutional neural net, the earlier layers are going to mimic the style, including the textures, the simple shapes involved, color combinations. These are going to be stored dispersed across the earlier layers. But the content is mostly going to be at the end. The content, the actual things we see in the image, is going to be up in these later layers at the top. And again, an example of that, the actual faces we're seeing are up here. They're up at this layer 3. The things that make up the faces are all down here. So, and it's also, the thing is, the style's going to be in several layers. The content's pretty much all just sitting at the very top. But the style is going to be all over the place. It's going to be at several parts of the network, dispersed across the lower layers of the network. So we really, if you want to think about this is all going to be about loss functions. This is very loss function heavy. So first, let's talk about how, with that loss function, we maintain the content of our image. So we need to do a content reconstruction, basically. We can this is all from the paper again. We can visualize the information at different processing stages in the CNN by reconstructing the input image from only knowing the network's responses in a particular layer. We construct the input images from these layers of the original VGG network. We find that reconstruction from lower layers is almost perfect, ABC. In higher layers of the network, detailed pixel information is lost while the high-level content of the image is preserved. That is what we want. We don't want to reconstruct the whole image of the content image because that's not helpful to us. We want to have the style be part of the image. So we're only looking to keep these high-level content pieces of the image around. And basically what they're saying here, in fact, I think, yeah, we talked about it here. So what we're doing for this part for the content part is we're going to take one of these upper layers. Specifically, I think I have it set not only here but also in the skeleton code as just being from block 5 conf 2 to reconstruct the content from that. And we'll see how the loss function is going to be involved with that soon. But basically, we're taking information from this layer here. This is where our content should be coming from. And you can also take it from parts of each of these if you want to, but the original version I give you is just going to be taken from here. Then we have style reconstruction. So, as they say here, on top of the original CNN representation, we build a new feature space that captures the style of an input image. Style representation computes correlation between the different features in different layers of the CNN. We reconstruct the style of the input image from style representations built on different subsets of CNN layers. Here's our numerous layers that we're grabbing from all across the network. This creates images that match the style of a given image on an increasing scale while discarding information of the global arrangement of the scene. So we're trying to keep the essence of the style without trying to bring any of the actual scenery, the actual content, the structure of the style image over, because we want the style image to just inform the style. And we do this by, we can extrapolate this by looking at the correlations of data between layers all across the network. In this case, we picked these 5. You can also change that in your labs, which layers you pick from. You might get better results, but these will give you good results. Maximizing the generated image. So given we're going to have a loss function, let's assume we have a loss function here that is going to help us move towards getting a better content style mixture. In this case, that means we aren't looking to do gradient descent on the weights. We're not changing the weights at all. We want to change the image. We're going to use the weights to learn things about the image. Because remember, this is a neural network that we're given at the start. Throughout this entire lab, we will not change the weights of the network. We're going to change the image itself. So we're actually going to run the gradient descent, like we've done before, on our image, on the network with respect to the input instead of with respect to the weights. And we're going to do that on an image that is random noise data. So basically our inputs are going to be content, style, random noise. We're going to gradient descent on the random noise. And we're going to do that with a loss function that takes into account these different layers of the network and takes into account trying to balance the style and the content from their respective images. Problem with this, and the only real problem, is that we need a network that already has been trained on a large image data set, a network that already knows images well. In fact, we need a few things. We need our input images, of course, content and style. We need a well-trained CNN. Actually, before we move on to this kind of more specific stuff, does anyone have any questions on this earlier stuff we've talked about? The high-level theory of the paper? No, not a Mountain Dew. All right, we'll move on for now. So we have input images, content and style. We're going to need a well-trained CNN that we can leverage its already existent weights to separate out the image. We're going to need a loss function for the content layer to maximize keeping the content without the abstract content of the content image. And we want to have a loss function that maintains the style of the style image without keeping the structure of it at all. And lastly, we're going to need some decent hyperparameters to work with, because otherwise this just won't work really well. The other thing here, Keras is not made for this sort of experimentation, really. I think Keras 2 is actually, or TensorFlow 2 with Keras is a little bit better, but this was not written specifically for that. So we're going to need to use Keras's lower level API. This is not actually TensorFlow, but Keras actually put... Keras's low level API is weird, because Keras is a high level API built on top of the low level API of TensorFlow, but then it also has its own low level API that's just kind of mostly directly transferring to TensorFlow. Regardless, we're going to use it here. Really, for something like this, it's almost better to do something like PyTorch. But we've already learned Keras, so we're going to stick with that for now. But yeah, we're going to be using, and that's, if you ever see a uppercase K in this, that's going to be for that. That is the little name we usually use for the lower level API of Keras. And it's going to allow us to do a lot more with it and access mid-level layers of neural networks. So yeah, as I was saying, it's the low-level version of a high-level version of a low-level API. Very fun. And it's basically TensorFlow. A lot of it's just TensorFlow, but bound to Keras functionality. And you can get it from this tensorflow.keras.backend.k, or as k. Or if you just have Keras installed and you're not doing it through TensorFlow, you can just do keras.backend as k. But how do we get the trained neural network? Let's get back to that. How do we get a well-trained neural net? Of course, we can write it ourselves. We can go through a whole process. As you know from the lab we just did, hyperparameter tuning is a non-trivial process that takes a long time a lot of the time. We can train it thoroughly and make sure we have this great model. We do hyperparameter tuning, try on running it on different super high performance computers with lots of GPUs, all that. But the easier option is we just steal VGG19. As we've said before, its weights are available online. It's a standard convolutional neural net, which is nice because then we don't have to deal with the weird things to do with like inception modules and stuff. So yeah, we can take VGG19 and use that, put our images through that without changing the weights at all, and gain this this separation of the image, which is very useful. So again, VGG19 has already been trained on a very large, diverse data set, specifically ImageNet. And I guess that's all I had on VGG19. So yeah, we're using VGG19 for this. We're going to take the weights, we're going to download them, and that's how that works. Content loss. This is going to be our loss function that is preserving content. So here's the actual math of it, and here's how they explain it in the paper. We're going to let P arrow and X arrow be the original images, or the original image and the image that is generated, and capital P prime and F prime are going to be their respective feature representations in layer L. So this is the filter output we are getting from layer L. And you can see here, you've seen this pattern before. This is just MSE. So what we're really doing here is we are, and this is the gradient of that, or the derivative of that, which you would be using for gradient descent, though I'll show you how you might not have to actually do that in this. This is the loss function we'll be using for loss content. Oh, it's the MSE between the feature representations, the final images, or the images, the outputs at the layer between the content and the content image and the generated image. So that's pretty useful. So and does everyone get why we are doing that? Is there any confusion there? Because I can try to explain it in a different way if there is. It's a weird concept. All right, I think we're good then. So let's talk content law, or let's see what that would look like in our code. Well, easy enough. Sum squares of gen minus content. If gen is our generated tensor and content is our content image tensor. So that's pretty easy to program. Next, we're going to talk a quick bit about something called gram matrices. We are not going to get into depth with these because this is I just don't want to. It's not something we need to know for this. At the very most basic level, we can look at it as a set of all possible inner products from a given set of vectors, which is nice. But the important thing to look at it as, it's going to help us find correlations, or it's going to calculate correlations for us between different tensors, between different outputs, and eventually between different these different layers that we're using to look for content images. So it's going to be our it's going to help us do that calculation. And notice here that I give you the code for that. You should use this code, and it is in the skeleton code because then it's real easy. Yeah, this is how you calculate those gram matrices. Just think of them, you can think of them for this as a black box function that is helping us to find the correlations between the style at different levels of the network. So for a style loss, we want to have a loss function measuring the error from the style image's style, how far we are from the style that we're looking for. And we can't do this directly from any one layer because the texture is all across the network, spread all across the different layers, mostly at the bottom, at the lower layers, but it's still in places all throughout the network. So we need to take multiple layers into account when we're doing the style loss. As the paper says, to generate a texture that matches the style of a given image, we use gradient descent from a white noise image to find another image that matches the style representation of the original image. This is done by minimizing the mean squared distance between the entries of the gram matrix from the original image and the gram matrix of the image to be generated. That's the important part here. So this is how they're doing it. They are minimizing the mean squared error, just like we did for the content, between the gram matrix of the original and the gram matrix of the generated. So that's interesting, and that's exactly what we'll be doing here. If you want to look at the math of this again, this is, again, we're just doing our MSE here, but it's a little bit different because we're including different representations at different layers. And it's going to let us do this kind of split of looking at the contribution of the different layers to the total loss. So here's that. Again, we have our, oh, this is actually not the gradient. I'm not giving you the gradient for this one. This is, each of these ETs here is going to be the mean squared error for one specific layer that we've chosen, layer L. And this is going to be between the gram matrices here of L and, or of GL and AL. So our original style image and our output image, generated output image. So again, this is kind of similar though to what we were doing before, except we're including these gram matrices into this. And we're also going to, at the end, once we have each of these for each of these different layers, we can then sum them up with a style weight, which we'll talk about in a bit. So here's our style loss. Here's your gradients calculation if you want to do it that way. But again, there's going to be an easier way that I'll show you in a bit here. And here's the style loss we're looking at. Again, this is not like perfect Python code or anything. You can't just drop this directly in and expect it to work 100%. But this is the pseudo code that you're going to be able to use to create the style loss. And you can see we're doing the gram matrix of the style image minus the gram matrix of the generated image. We are squaring that. We're summing it. And then we're doing our little multiplier here, or divisor, I guess, as 4 times the number of filters squared times the image dimensions squared, image size squared. And then the total loss, this is where they come together. So it's a lot easier to do these things when you have one loss function that's doing the whole thing instead of having multiple loss functions. So we're going to combine both of these loss functions into one. In this case, we're going to have L total loss, is going to be the weighted sum of content loss and style loss. And these weights are actually hyperparameters that you can choose yourselves, or alpha and beta. So quick question for anyone willing to answer. What would happen if I made alpha very big and beta very small?
Then it would carry.
I'm sorry, say that again?
Wait. Sorry, I thought I heard somebody else, but I just realized it was feedback. If alpha was very large, then it would be focusing more on content than style. And it would be the same way the other way around.
Very good. Yeah, so this is going to let us choose whether we're going to have an image that's a lot more like the content image and just touched by the style, or very stylistic and doesn't have much to do with the content, or some combination. This is going to let us, these are the little dials we're using to tune in on what we want our neural network to focus more on. So, and who said that?
Nicholas Rose.
Cool. All right. So, we have our function, our loss functions now. We have VGG. We're going to need our image processing pipeline. We've used this quite a bit already. We're going to need to change it a bit, though. We're not doing the normal tasks that we do where we are playing inputs and outputs against each other in a supervised learning sort of way. What we're doing here is kind of a hacky version of that, an offshoot of that. We're actually doing something a lot closer to unsupervised learning for this, though the training of VGG was supervised at the beginning. We're doing something a bit different than is standard, so pipeline's going to need to change. Final evaluation we can only really do as humans because it's not really, there's not a great metric for how closely two styles are. Like, you can do it, but it's not going to really help you much. So really, that evaluation needs to be done by us looking at the image and saying, okay, this looks stylized or not. So we're just going to remove that step from our pipeline that we usually do. We also already have our model, so we don't need to train it. It should be already trained. We just need to build it and have it already. So we only have 3 steps we need. Get the raw data, pre-process it. Technically, we could throw like building your model in here too. But that would just be taking VGG and putting the weights that you take from online into it. And lastly, we have style transfer, actually doing this process and doing a gradient descent on the image with these loss functions that we have now. So here is what that is going to look like for us here. This could actually be a little bit more efficient if we wanted, because the transfer image right now, we have our content, we have our style, and then the transfer image, I think right now I have it still being pre-processed in that way. We could probably do it without that, but it works. It's already finished in the code of the skeleton code, I think. So process here, we get the raw data, we pre-process all that raw data, and we do a style transfer on it. Here's our C data, S data, and T data, and it's just going to go through the style transfer process and save those images, and then we're done. Gram matrix, we talked about this. It is already in your skeleton code. It's going to be instrumental in your style loss function, but that's mainly it. There it is. We need our list of layers that we're going to be drawing from. In this case, I've given you 5 you can use from for style and 1 for content. Feel free to change these if you want. Even maybe add other ones for content and see what happens. I would definitely add these higher ones, though. This block 5 conf 2 is pretty high up there because it's in block 5. The other thing we need is an optimizer. Now, we've done a lot of optimizers like with Atom and stuff, and to be clear, you can do that. It might be easier in this lab if you actually use an optimizer from SciPy. I picked this one, which is limited memory BFGS. It is it's not the best optimizer for a lot of situations, but I think this was the one they used in the paper. And the nice thing with this one that we're getting from SciPy here is it lets us pick what we're optimizing instead of just optimizing on our weights, which is helpful. Because again, we're not optimizing our weights, we're optimizing our inputs. This is what that function is going to look like. And here's some of the important fields you're going to need to fill in. There's two required fields, first of all. You're going to need a loss function that is going to you're going to need for this to make a wrapper function to make this work. But and that can be a whole pain in the butt, but it should be possible to figure out when you look at some examples of how fmin of GS is used. But you'll need that loss function to calculate the loss. You're going to need the data that you're going to optimize. In this case, it's going to be our image tensor we give it. This f prime is actually going to be our gradient function. That is going to mostly because we're calculating our gradients and our loss at the same time, you're going to want to make these two wrappers around the same function. You can use an object or global variables, but you'll have to find a way to basically actively use both of these if you want to do it right. I might in the future change this lab to use PyTorch or something, because we go a lot out of the way to make it work with Keras. But yeah, it's a bit of a pain working with this kind of function. But there's examples on it online that you can find pretty easily, so I would definitely look those up of using this SciPy optimizer. Or you can try to use your own optimizer. Use one of the normal standard Keras ones and just get it to work that way. In fact, one of our best style transfers we ever got in this class was by a guy who I think he actually ended up choosing a different optimizer, and he had these super lifelike images of his dog. It was crazy. Well, I mean, they were lifelike. They were real images of his dog, but they looked painted. They looked like they were painted in the style of Starry Night. It was really cool. And yeah, maximum number of iterations. That's just going to be how many times it's going to optimize on. The thing is, this part is going to be the longest part for this lab. It's going to take a long time to run. I mean, not to write necessarily, but just to run this thing's going to take a while. When I originally wrote this lab, in fact, it took 4 or 5 hours to run it on my laptop, which, I wasn't using GPUs or anything, so that's part of it. But I know that, like in the previous labs, it's been like, if it takes 20 minutes, that feels like a long time. If it takes 5 hours for this lab, that's fine. It's style transfer's hard work. And if you want to make sure that it's doing it, and you want to make sure that it's not, if you want to do it for debugging purposes, maybe start with smaller images or scale down images or something, and then see if it's doing something vaguely like style transfer before you test it on the big images, because we're optimizing on the image, so that is the data that we need to be, that's going to really slow us down. Here's what I was talking about earlier. You can get your gradients, you can calculate your derivatives in the way that I showed you, or where I showed you the math that was already behind it. You can do that. You can actually implement that math just like you did in the custom neural network before, and that'll work just fine. But Keras backend has this nice function called gradients, where if you give it a loss function and variables, it will actually calculate those gradients for you. And that is life-saving. It's really good. So you don't have to actually... You can make that loss function, or make all those loss functions, and then instead of going about calculating the gradient of those loss functions, and then so you can do the backprop on them. You can get them this way. You can get them with tf.keras.backend.gradients. And the other thing is, of course, getting VGG. So TensorFlow actually has that built in, of course. It just has the whole VGG available, which I like. You can import this and have this VGG19 little library thing. And from that, you can get a version of VGG that we're not including the top of it. This include top is saying the head of the network, the fully connected part. So this is just the convolutional bits. And we're asking for the weights when it's trained on ImageNet. So that's super useful. There's our whole model done. Good stuff. And the last little quick, I don't know if even a tip as much as like a hint. And I might drop more of these as we go on Piazza. Once you get to the point, and you might not understand this right away, it's going to be more useful to you once you actually get to look at the skeleton code. We have our gradients. You're going to calculate those however you do, maybe with k-dot gradients, maybe by your own. And you're going to want to, because fmin BFGS needs kind of a wrapper function to follow. Well, not just fmin BFGS. Because we're using our data graph, we're going to need to wrap these our gradients that we get from these loss functions that we made into a Keras function. So once we've calculated this as gradients, we put it on with our loss variable here. Again, this is not actual loss. This is part of our graph. And we can append that on with our outputs here and put that into this k-dot function, which is going to be an internal function of the graph. And yeah, this is going to end up being our stand-in for our loss function, our wrapper for it. You will probably actually need that in a second layer of wrapper. That's going to be between your func argument here and your f prime argument here. But yeah, this could be useful to have in there. So the thing with this lab overall, though, it's a tough kind of idea to get around. The important thing here is if you have questions, if you have trouble with it, first step, read the paper over. You should absolutely, this lab, part of the idea is just that you read the paper very carefully. So read this paper, read it several times, annotate it if you need to. Whatever you can do to really understand the concept of it super, super clearly. And then when it comes down to actually doing the implementation of it, you can use any resources you need. If you need to go Googling around for other similar things, go right ahead and do that. Nothing wrong with doing that at all. This is the previous labs were a bit more like normal labs. They're a bit more along the lines of apply the things that we learned directly in lecture. This is a bit more independent. This is a bit more of looking at a paper, learning to look at these papers and synthesize what they're saying and implement what they're saying. So that's the kind of the idea behind this. I've got some useful links here, especially. Yeah, I highly see if you don't read the paper at least once, it's going to be hard for you to grasp the ideas behind it. It's an important paper. It's useful. And it's also not spring break. I really need to check these slides better before I start doing them again.
I wish it was spring break.
I wish it was spring break, but yeah, it's. Well, this time we don't even have fall break. We're just stopping. Well, we
I don't
have
even
fall
think we
break,
get
but it's
spring
just.
break. The tentative spring semester schedule's been posted. We just get 3 quote unquote reading days at the expense of getting rid of more than 7 days of break.
Yeah.
So
Oof.
It's currently an option out to get a reading day this.
I don't even think we get Martin Luther King Day off anymore. It's just gone.
Yeah,
We don't
get
start
any-
till after Martin Luther King Day, I think. Like the
Oh,
day
okay.
after.
I guess that just about do it then.
Yeah, I think we start on like Tuesday.
So
It's 'cause it's a
when was
Tuesday.
supposed to be the October break? Was this going to be this week?
I think so.
Yeah.
Yeah, I forgot
Yeah.
we had October break.
It would normally have been on, I think, Monday, right?
This past Monday and Tuesday.
Oh. Huh. I could have
There's
used a break
petition
on
out to
Monday
get a
and
reading
Tuesday.
day, but I don't know if that'll happen.
Oh, the second part is also a lie because this lab. I mean, it's not a lie. It's true. It will be posted before Friday. It's already been posted. So yeah, yeah. That's it for that though. And then